Okay, let's start this lesson by looking at some names that are used in the IUPAC nomenclature with substituted benzenes. And that's simply some things that you just got to know. It's the easiest way to do it. You just got to know it. So this is called toluene, styrene, phenol, aniline, nitrobenzene, anisole, benzoic acid, benzaldehyde, and acetophenone. Flashcards would be a great way to do that. Or just watch that video about 1,000 times over. When we're naming polysubstituted benzene, so something that's not just one substituent, there's different ways of doing that. But either way, you need to know how to identify some certain positions relative to whatever substituent that you have from above that's on that benzene. So if that's what we've got, that's aniline, right? This is just aniline. I'm just highlighting the hydrogens around here. So if this is aniline, these would be the positions orthogonal or ortho to that NH2. These would be the meta positions. And this is the para position. So think of a periscope, how it goes to the opposite side of where a submarine is, right? That's going to be the opposite side. This one's the middle, and that one's ortho. So when we go to name things with just two substituents, and this only works for things with two substituents, you have to take one of the names that we have up here, except for toluene. Toluene we actually don't use that much in there. But if we have this, like this would be aniline, we can call this, that's ortho meta. So we could call that meta-ethyl aniline. Now that is the complete same thing as 3-ethyl aniline. And if you'd rather call it 3-ethyl aniline, that's totally fine. But in our next sections, we're definitely going to need to know that these are the ortho positions, these are the meta positions, and that's the para position, okay? Okay, so when we're naming things with more than two substituents, that's when things get a little bit more entertaining. In this case, I'm going to look for the root of what we have up top, and that is, this is again aniline. So that means that we have a bromo substituent and an ethyl substituent. We want to name this as, number this so that we have the lowest numbers possible, so 1, 2, 3, 4. But bromo comes first in the alphabet, so it's 4-bromo, 3-ethyl aniline. Now in this case, phenol is our root of our name. And we have a choice if we're going to go to bromine or chlorine first. Well, bromine wins because it's higher in the alphabet. So that means it's 3-bromo, 5-chlorophenol. This guy would be 3-bromo, 2-chloro, nitrobenzene. Good. So now we know how to name these things a little bit. So let's talk about how awesome benzene really is. Benzene it's awesome. I mean, it's awesome. Well, it's got special traits because it's something called aromatic. And here's what we're going to talk about a little bit more in this lesson is aromaticity. Now let me give you a little bit of a background of that. It doesn't smell. There's no smell pertaining to this particular compound or this family of compounds. I actually thought that when I was in undergrad, but that's not really it. It's more like these guys do something special that is an overall lower energy. So let's look at benzene here, and I'll explain what I mean. When you take these double bonds, that's a resonance structure, right? We can add electrons to sort of push these electrons around, arrows to push these electrons around to give you this. Well, each of those carbons has an sp2 hybridization. In other words, they have an open p orbital. And what that allows is for the open p orbital to sort of talk to each other. They're resonating to each other. And if you look at the electron cloud around benzene, what it really looks like is a Paladine hamburger, okay? So you got a donut on top, a donut on bottom, and the benzene, which is the carbons themselves, are on the inside. Because keep in mind, all those sp2 hybridizations, all of those carbons are on one plane, right? Because they're trigonal planar. So the bonds are stood, it's a flat molecule. And what we find is that when all of those electrons and those p orbitals can be what we call delocalized or spread, they can just share space among the entire group. That's a special type of lower energy molecule called an aromatic compound. And so we found out that there's this family of compounds that are aromatic, have certain traits to them. To be aromatic, they must have all the atoms in a ring. And if there's atoms outside of the ring, they don't count, okay? So don't worry about what's outside the ring. Just worry about what's inside the ring. And each atom must have unhybridized p orbitals. So in other words, you have to have this open guy, like what we're seeing up here, okay? The molecules must be planar. So you have to watch that, because when you get some really big types of rings like octane and stuff like that, octenes, they actually bend, and so you can't actually have a flat scenario just because of the bond angles. Even an sp2 won't work. And then we apply something called Huckel's rule. Now this stands for a 4n plus 2, where n can be anything, and it has nothing to do necessarily with the size of the ring. And so that's another thing that I know I misunderstood when I was an undergrad. But let me simplify that for you even more. If you can find that there are an odd number of electron pairs that count, and we'll talk about what that means in just a minute, then it applies to Huckel's rule, and therefore it can be aromatic, okay? Now, if we find instead that we have an even number of electron pairs, that's the opposite. That's actually something that's even higher in energy and not lower in energy. So since that's higher in energy, that's something that we actually really try to avoid. So let's look at some examples here. Notice that I have positive charges both here and here. Well, what does that really mean? It means that you don't have a bond there, right? A bond is missing. That could be represented easily as an open p orbital. This, by having open electrons that are there, those can reside in an open p orbital. They don't necessarily reside there. You might have a different type of hybridization in other molecules, but the reality is that for these compounds and for these structures, it's overall lower energy for the entire molecule to have that open p orbital, and that's the reason why it goes in that route. So here we go. We've got 1, 2, 3 pairs here. Heck, aromatic. Only one pair there. That's an odd number. Aromatic. 1, 2, 3. 1, 2. This one still counts because it's a lone pair of electrons. Those count. And down here we have 1, 2, 3, 4, 5. That's odd. Everything's flat. We're good. All those are aromatic. Now, let's go over to anti-aromatic. There's only 2 pairs of electrons here, and here, and here. Those are anti-aromatic compounds. This seems crazy to me because these bond angles are killer, right? But this one's 90 degrees, which is still pretty bad. If it tells you anything, we can't isolate this, but we can this. We can use this. So anti-aromatic compounds, definitely higher energy. There's a reason why they're higher energy. You can kind of think of this as this is perfect harmony musically, and this is kind of like screeching down your nails on a chalkboard. Or better yet, what ends up happening in some ways that we kind of understand it is that the waves, like if you consider a wave, they don't match up. Like you can't actually match them. The one's in one position, one's in another, depending on how you think about things. Okay, not to go into too much detail there. This is an sp3 carbon in each of those, which means that there's no open p orbital. And what that means is that it's not either aromatic or anti-aromatic. It actually doesn't even fit the first rule, and that is that you don't have an open p orbital. So they're just simply not aromatic. In this case, these electron pairs are localized, so they're isolated here or here. In this case, they're conjugated, so they're delocalized here, but they're localized here. But that's really all they are at that point.